Our mission is a regolith volatile extraction and return expedition, or ReVERE, and welcome to our presentation. Let's meet Team ReVERE. I'm Sabrina.
I'm Caitlin.
I'm Brandon.
I'm Matthew.
I'm Rob.
I'm Jacob.
And I'm Asha.
We are competing in Theme 5 to create a new architecture to perform lunar sample aggregation, analysis, and return to the ISS. The mission will commence in 2022 and operate by 2028 with a yearly billion-dollar budget. The driving need is to further our scientific understanding of the Moon, which will be achieved from a lunar sample return mission from various locations. The following mission goals are derived from the needs statement. The threshold mission is a lunar regolith sample return. The mission goal is to return 30 kilograms of regolith and unpreserved volatile samples from various locations. Mission success is a regolith sample return from various locations with different geological profiles and of neutron suppression zones. The following slides will focus on lunar science. Science goals are derived from the Decadal Survey, Artemis, and League. Primary goals determine the threshold architecture. Secondary goals add complexity and risk. Volatiles are unstable and can sublimate introduction challenges from the point of extraction, storage, and transport. Volatiles also require acting cooling mechanisms for preservation, significantly increasing the mass budget. To minimize risk and increase the usable sample return, volatiles will be collected but not preserved. Sample return heritage from Apollo, Chang'e, and Luna are shown with their respective geological profiles. Moon ages from youngest to oldest are Copernican, Eratosthenian, Imbrian, Nectarian, and pre-Nectarian. Combined heritage shows we've only researched 5 of 49 profiles and middle-aged samples along the near side, which is why we focus on the South Pole. A South Pole mission is coveted primarily because it's unprecedented in its potential for resources. The Decadal Survey proposed a sample return mission from the SPA because it allows us to study the Moon's origins, and observations from orbiters have revealed regions of significant hydrogen and possibly water using neutron detectors, which ID hydrogen deposits by creating resource maps of rich neutron suppression zones, since hydrogen atoms lack neutrons in their nucleus. The polar environment also traps volatiles, giving us clues of the Moon's evolution and resources for human habitation and industrialization. Lastly, the poles have smaller temperature fluctuations. A risk analysis of mission success was done on the initial architecture of one Lunar Transit Vehicle, or LTV, and one rover, resulting in increased chances of failure. To mitigate risk, an additional LTV or AL, additional rover or AR, and sample collecting LTV or LC were used. To decrease risk and increase sample return success, a redundant architecture of 2 identical LTVs capable of sample collection, each with 2 identical rovers, is established. 2 landing sites of interest, or LSI, were chosen, one between Shackleton and Shoemaker craters, and the second between Shackleton and Faustini. Rovers will nominally travel for 6 months to return 30 kilograms of samples. Due to irregular illumination, uncertainties, and typical rover speed based on Mars and Chang'e 3's U2 rover, which traveled 10 kilometers in 3 months, a contingency plan was designed with max travel of 1 year. If rovers experience any complications, they'll immediately return for aggregation. Waypoints for each LSI were designed to not exceed a one-way distance of 9 kilometers and showed 10 locations of recommended sample collection. Additional points will be determined by the rover tool suite. Waypoint A will travel to the first waypoint of sample collection, return for aggregation at the LTV, then proceed its route while B travels as planned. Waypoint specifications are also shown in the table above. Waypoint D, like A, travels one location then returns for aggregation. This contingency plan establishes redundancy and ensures sample return success in the event the LTV cannot collect samples upon descent. Each LSI has strict constraints to satisfy the mission goals, science goals, and establish good power, communication, and rover travel conditions. When combined, both LSI provide 4 unique geological profiles, 2 of which are pre-Nectarian, the oldest period on the Moon. Asha will now discuss her CONOPS diagram.
Now that we have an understanding of where we are going and why, let's look into how. Launching on a Falcon Heavy, the assembled lunar package, or ALP, enters a parking orbit before its translunar injection maneuver. By day 5, the ALP will enter a 100-kilometer circular lunar orbit, enabling the 2 lunar transfer vehicles to separate from the LCS and prepare for descent. On day 7, the 2 LTVs will deploy their 2 rovers to start sample collection. Note that extra time in the rover operation schedule is built in to account for issues on the lunar surface and delays in launch. The samples aggregate at the landing site in the LTV, and by day 382, the lunar transfer vehicle launches to rendezvous with the lunar communication satellite. After trans-Earth injection, the LCS will rendezvous with the ISS, undergoing a track and capture procedure with the Canadarm2. Finally, decommissioning occurs by day 392 via atmospheric entry of the LCS. Let's dive into more detail about launch and transit to the Moon. Launch is planned for early 2027 on a Falcon Heavy rocket for a cost of $150 million. The expendable Falcon Heavy configuration can carry approximately 21,000 kilograms to the moon, giving us a mass margin of 7,626 kilograms. In the Falcon Heavy fairing, the ALP will rest on top of an upper stage adapter with plenty of room to spare. The overall dimensions are shown and put an approximate reference to the size of the Falcon Heavy fairing. On the landing pad, we expect the ALP to have a mass of approximately 13,373 kilograms. Since the translunar injection is performed by the Falcon Heavy upper stage, the payload mass remains the same until lunar capture. The LCS will be in the main propulsion unit, applying an 830 meter per second delta V to move the payload into lunar orbit. The lunar landed wet mass and the ascent mass are also shown. Finally, the wet mass of the LCS with samples is approximately 3,372 kilograms, accounting for the 4 kilometers per second burn needed to perform a trans-Earth injection and rendezvous with the ISS. Now Brandon will discuss our translunar trajectory.
Following launch, the ALP will be placed into a circular 200-kilometer parking orbit with the following orbit elements. This parking orbit was selected for a launch date of January 1st, 2027, using a NASA GMAT simulation. Specifically, the argument of periapsis and the right ascension of the ascending node were chosen to ensure the transfer line of apsides aligns with the moon and to inject the ALP into a polar orbit upon arrival. The translunar injection maneuver will be performed at the periapsis of the parking orbit by the Falcon Heavy upper stage. Moving to the ALP's transit to the moon, this will take place between days 2 and 5 in our schedule. This portion consists of the translunar orbit injection, or TLOI maneuver, in addition to possible mid-course corrections. For the transfer to the moon, a direct transfer without Earth phasing orbits was selected. This slide depicts a simulated direct transfer orbit to the moon with a time of flight of about 4.12 days. Now I'm going to hand it off to Caitlin to discuss communications and power during lunar transit.
NASA's Gateway is an outpost orbiting the moon that supports both human and robotic exploration as part of the Artemis program. The power and propulsion element provides power and communication support, among other things. We know that this exists and could be an option for our mission, but we also have developed an independent solution for this project. Based on bands available, time windows available, and price, we've chosen to use the Near Earth network, which serves various types of customers and missions. Based on heritage, we have chosen to use S and Ka bands. The S band will communicate at 2 GHz and the Ka band at 34 GHz. The communication window requirement for our mission during transit is based on the Lunar Reconnaissance Orbiter and is therefore 30 minutes every 12 hours. The requirement for operations is based on the Curiosity rover, since we will be on the surface at that point, and is therefore 3 30-minute windows every 24 hours. These windows include the time required for both uplink and downlink. Now moving on to power, shown here is a heritage-based power budget for transit mode, which is just the normal mode used during transit as long as nothing is going wrong. As you can see, thermal and attitude control are expected to use the most power, while propulsion is expected to use the least. The total allocated power is 250 watts, and the allocated daily energy is just under 7 kilowatt hours. Shown here is a power budget for safe mode. This is for during transit if something goes wrong and we need to drastically reduce the power usage. Power-wise, command and data handling and propulsion were cut completely, attitude control was reduced to almost zero, and communications and thermal were cut in half. These reductions would allow the spacecraft to still function at a very basic level while only using 1/5 of the power used in transit mode. Based on heritage, we have chosen batteries and a solar array for our power sources. The battery will be capable of providing the allocated daily energy and will be recharged by the solar array every 24 hours. The solar array will have the ability to move and continuously track the sun. These power sources were sized based on the information discussed already, as well as some additional numbers chosen based on heritage. The solar array will have the allocated power discussed in the transit mode power budget, which results in a mass of 6 kilograms. This will be used to recharge the battery, which will allow for the allocated daily energy calculated in the transit mode power budget. This will put the batteries at about 35 kilograms. Next, Brandon will discuss lunar orbit insertion and descent.
Lunar orbit insertion, or LOI, will occur at around day 6. This consists of the lunar orbit insertion maneuver to inject the ALP into a circular near-polar orbit. Using the LCS's primary thruster, the ALP will insert into a circular near-polar 100-kilometer altitude orbit with the following elements upon arrival. Up to this point, the ALP will still be intact and nothing will have separated. This circular orbit will function as a parking orbit for lunar transit vehicle deployment, as well as a staging orbit for the LCS to transition to the final communications orbit. The next step in our plan is lunar descent, which consists of LTV separation from the LCS, followed by the descent orbit insertion maneuver. This will later be followed by powered descent and finally surface touchdown. Apollo mission heritage forms the basis for the LTV descent and landing procedures. Following separation, the first LTV will perform the descent orbit insertion maneuver to enter an elliptical transfer orbit that reduces the altitude of the LTV. At the periapsis of this descent orbit, powered descent will begin, which will be a period of continuous propulsive maneuvers to reduce the orbit velocity and guide the LTV towards the landing site. The second LTV will follow a similar procedure after the LCS and second LTV complete one orbit after the deployment of the first. With the LTVs now on the surface, we will discuss lunar surface operations. Following deployment of both LTVs, the LCS will maneuver to its final communications orbit by following a Hohmann transfer. The communications orbit selected for the LCS during lunar operations is a circular near-polar 750-kilometer altitude orbit. This orbit was selected in order to minimize delta V to maneuver into this orbit. Moreover, this orbit does not require any station-keeping maneuvers throughout the duration of the mission. While this polar orbit does not provide optimal communications, the communication requirements for the mission are satisfied by the coverage provided by the near-Earth network. Next, Caitlin will discuss communication with the LTVs and rovers.
We will also have the ability to directly communicate with ground stations for a portion of our operations period. This leaves us with three communication options: direct communication between the rover and ground station, using our lunar communication satellite as a relay, or using any other lunar orbiter, such as the Gateway Outpost, as a relay. To sum up our communications discussion, we have a lunar communications CONOPS diagram. First, let's take a look at the elements shown in this diagram. We have Earth at the top and the lunar surface at the bottom. On the lunar surface is a lander on the left and two rovers in the middle and on the right. We will actually have two landers, each with two rovers. Shown in the top corners of this image is our one orbiting lunar communication satellite. Now let's look at the communication links between each element. First, look at the green arrows on the left and right sides of the screen. These show the uplink from the vehicles on the lunar surface to the lunar communication satellite. These will be S-bands. Next, look at the blue arrows. These show the downlink between the same vehicles and are also S-bands. Finally, we need communication between the lunar communication satellite and Earth. These are shown by red and orange arrows at the top of the screen, which will be Ka bands. Next, Jacob will discuss the Lunar Rover design.
Once the LTVs have separated from the APL and begun their final descent maneuvers, the legs will be deployed and the red rocket will perform its final burns. After the lander has successfully touched down, the wheels on the rovers will be deployed and the struts connecting the rovers to the LTV will disconnect. At this point, the rover is ready to begin its mission across the lunar surface. Once the rovers have maneuvered away from the LTV, the upper solar panel can be deployed. It is on a 3 degree of freedom mount so that it can be positioned to maximize sunlight exposure no matter the direction the rover is facing. At this time, the S-band antenna will also actuate into position. This antenna will allow for communications with the LCS as well as with the near-Earth network so that the rover can be remotely operated. Once the rover has reached a point of interest, the wheels will lift up and lower the main rover body to the surface. The sample collection mechanisms rely heavily on technology from the Perseverance rover. The drill, vacuum-sealed canisters, and storage trays are all based on the Perseverance design, with the only big change being the size of the robotic arms. After the rover has been lowered, the lower robotic arm, with 3 degrees of freedom, positions the drill head in the location where the desired samples are, as seen in the animation on the left. The robotic arms are remotely controlled and monitored by the camera on the rear of the rover. The drill head contains bits to collect both regolith and volatile core samples. After the desired sample has been collected, the lower robotic arm positions the drill so that the upper robotic arm, which has 5 degrees of freedom, can collect the sample canister, as seen in the animation on the right. After the drill has been moved to the sample canister collection position, the upper robotic arm maneuvers itself such that the canister sealing mechanism is above the drill head. This motion is illustrated in the animation at the top right. The sealing process is based on the sealing process used by the Perseverance rover. After the sample canister has been sealed, the upper robotic arm lifts the canister out of the drill head, as shown in step 1. Next, the upper robotic arm moves the sample canister out of the way of the sample drawer. In a similar fashion, the lower robotic arm moves the drill head out of the sample drawer's way. These maneuvers are seen in step 2. The sample drawer is then opened and the upper robotic arm places the sample canister into its place in the drawer, as shown in step 3. In order for sample identification, each canister is marked with a 3-digit serial number that is recorded by the camera after the sample has been collected. Each rover will have 3 main tools for collecting samples and analyzing the lunar surface. As mentioned previously, sample collection will be handled by the Perseverance drill. This drill system is capable of collecting and storing both regolith and volatile core samples. In order to analyze the lunar surface, two separate spectrometers will be used. The first is the Nervous Neutron Spectrometer, which will be used to detect hydrogen within the lunar surface. The second is the M-Solar Mass Spectrometer, which will be able to classify the state of the hydrogen found. The nominal power budget for the rover can be seen here. Of interest is the thermal system, which has no power draw since it is a passive system using a lightweight radioisotope heating unit, which will be discussed later on. The power sources for the rover are a main battery, a backup battery, and solar panels to charge these batteries. While in operation, the rover will have 4 different operating modes. The first is the roaming mode, which occurs while the rover is navigating between mission waypoints. Once the rover reaches a waypoint, it enters into the science mode. During this mode, the rover will be drilling and collecting samples. The third mode is a safe mode in case of mission anomalies. Only critical functions are powered in this mode to ensure that the rover can get back to the LTV. The last mode is the dormant mode, in times when there is insufficient illumination for the rover to fully function. Only limited computer function will be powered in this mode. Now Rob will discuss the thermal analysis for the rover.
For thermal analysis, the software we used was the AutoCAD add-on Thermal Desktop by CNR Technologies. The lunar environment was generated using properties based on previous lunar thermal analysis papers, and the materials and heat loads were taken from our own design specifications. The figure on the right shows the AutoCAD rendition of the rover. The internal layout of the rover is a large factor in thermal convection, so we defined it with thermal loads in mind. The figure on the right is a bird's eye view of the internal layout of the rover, with the table on the left acting as a key to label each component in the figure. These components are simplified into simple 10 cm by 10 cm squares in the thermal model, as is common practice for thermal desktop analysis. To simulate realistic convection between lunar surface and the rover, our thermal model includes a 100 meter by 100 meter square of lunar soil with the rover placed in the center. This patch of land is composed of a layer of dust and a layer of soil, each with different material properties defined by previous heritage studies and missions. A list of these properties is shown in the table here. The thermal control system we have implemented is the simple lightweight radioisotope heating unit, a unit used previously on missions such as Galileo, Cassini, and others. The heating unit uses the natural decay of plutonium-238 to generate heat to keep the rover temperature in a safe range, and is designed to withstand the jostling and jolting of a lunar rover mission without the release of radioactive isotopes. An additional benefit is its lifespan of 7 years past its initial fueling, which fully covers the scope of our mission. To go into a little more detail on the LWRHU, it consists of a 2.7 gram pellet of plutonium dioxide surrounded by a clad of platinum 30% rhodium alloy and an insulation system of pyrolytic graphite that acts as the effective line of defense against radioactive contamination. It also includes a vent that allows for the release of gradually produced helium gas, a natural byproduct of radioactive decay. Some more specifications, including the physical dimensions of the LWRHU, are listed in the table on the right. Our first thermal analysis case was in total darkness, as can be expected for days at a time on the lunar surface. As the figure on the right shows, the range of internal component temperatures is fairly low, with temperatures around negative 58 degrees Celsius. These temperatures are survivable but inoperable, which indicates the need to implement some kind of dormant cycle like the one discussed in our power budget. Our second thermal analysis case was the sunlight case, where the rover can expect to experience some time in the sunlight, warming it up significantly. In fact, the temperature range is a little bit too high at around 76 degrees Celsius. However, the only components experiencing that range are the motor for the drill and the batteries, with the spectrometers experiencing a safer temperature range. This indicates a need to devise some sort of thermal insulation for the batteries and drill motor, as they are the most pressing issues in terms of temperature range. Perhaps the largest obstacle in using the lightweight radioisotope heating unit is actually obtaining the fuel source. Thankfully, NASA and the U.S. Department of Energy restarted plutonium-238 production in 2015 and have since generated at least 250 grams in stock. Although the exact process of obtaining plutonium for space missions is not publicly accessible, in the event our mission reaches development stages, it is likely to qualify for the amount we need. The cost of plutonium for the scope of our mission is about $100,000 for a 10-gram requirement across our 4 rovers. Next, Matthew will talk to you about the lander sample aggregation.
So this is the sample aggregation phase. Once the rovers have collected their desired samples, they back up to the LTV and utilize rails to slide the samples into an open port on the sample container. The mission goal is to collect a total of 30 kilograms of samples. The sample container we use is visible here in the bottom right. This slide shows a method that was utilized on the OSIRIS-REx mission to collect a small sample immediately after touchdown. The foot of the LTV will sink into the lunar regolith and collect a sample. The sample will then be dragged into the body of the LTV through a wire. This will allow us to collect at least a small sample before deploying the rovers. Now this is the ascent and rendezvous phase. Once the samples have been secured inside the body of the LTV engages its thrusters and detaches its legs, descends to a lunar orbit, ultimately to dock with the Lunar Communications Satellite. Both the LTV and LCS are equipped with attitude control systems to plan for the docking maneuvers and to make the necessary adjustments in order to rendezvous and for the LCS to obtain the sample containers. So this animation here shows the LCS grabbing the sample container from the LTV, makes the necessary adjustments, lines up the universal docking ports, makes the connection, and the LTV then releases the package, leaving it only attached to the Lunar Communications Satellite. And this is an animation showing the second sample container being collected from the second lunar transit vehicle. And once the LTV has completed its mission of delivering the sample container to the LCS, it'll remain in lunar orbit until it eventually crashes into the moon. So on the left here, we have the universal docking port that is on both sides of both sample containers and located on the front face of the LCS. So this is what's used to attach the sample containers to one another and to attach the sample container to the LCS. And on the right here is Lunar Communications Satellite with both of the sample containers stacked on top of it. These are the rendezvous sensors we'll be using for our mission: the Star Tracker, TriDAR, and VisCam. Star Tracker is to understand the attitude of our spacecrafts. TriDAR is used for range tracking to plan that rendezvous between the LTV and LCS. And the VisCam will be used for proximity operations once they get very close to one another to plan the precise maneuvers required to line up the universal docking ports. Here are the dimensions of the Lunar Communications Satellite. The total volume of the LCS is about 7 cubic meters. And here is the dimensions of the Lunar Transit Vehicle. And on top, you can see the visible RCS thrusters. There's 4 on top, 4 on the bottom, and 4 on the sides for a total of 12 unidirectional RCS thrusters on the LTV.
Now we will discuss the trajectory design portion of the surface ascent and rendezvous segment. First, the LCS will descend from its 750-kilometer circular communications orbit to a lower altitude circular orbit, the altitude of which will be determined to minimize the delta V needed for rendezvous maneuvers. The first LTV will then launch from the surface into a 90-kilometer circular orbit. Once the LTV is in orbit, the LCS will perform targeting maneuvers to rendezvous with the first LTV. The second LTV will follow a similar procedure to rendezvous with the LCS, which is already in a 90-kilometer circular orbit. Based on a delta V minimization analysis, the LCS will first follow a Hohmann transfer to descend to a 198-kilometer altitude circular orbit. From this rendezvous initiation orbit, the LCS will begin rendezvous when it is about 8 degrees ahead of the first LTV in its orbit. Once the LTV rendezvous with the LCS and transfers its sample package, the LTV will perform a small separation maneuver using its reaction control thrusters. This process, albeit with the LCS already in the 90-kilometer orbit, will be repeated for the second LTV. Finally, with the samples now in orbit aboard the LCS, we will discuss the return to Earth and subsequent rendezvous with the ISS. This portion of the mission includes the trans-Earth orbit injection maneuver performed in lunar orbit and the Earth orbit insertion and ISS rendezvous maneuvers. In returning from the moon, the LCS will follow a direct transfer. To mitigate the risk of collision, the LCS will be injected into orbit 20 degrees ahead or behind the ISS. Once the LCS catches up with the ISS, rendezvous will begin. To reach the 2.5-kilometer hold point, after which the LCS will follow Dragon rendezvous procedures, the LCS can either approach from above or below. This describes the different approaches that will be followed by the LCS in returning. Approach 1 will be tailored to minimize the delta V needed for return and rendezvous. Approaches 2 through 4 describe the different rendezvous standoff positions, followed by Dragon in docking with the ISS. The diagrams included here are contour plots used to select the trajectory conditions that would result in a minimum delta V, both for approaching the ISS from above and below. Overall, the minimum total delta Vs for both approaches are approximately the same, meaning both approach trajectories are feasible choices. Because of the slight savings, the below approach was selected. On the right of this slide is a proximity operations diagram comparing the 2 approach trajectories, as well as the location at which the LCS will then follow a nominal approach trajectory. Once the LCS reaches the 2.5-kilometer hold point along the R bar of the ISS, it will then follow a nominal approach established by SpaceX's Dragon. The nominal approach, illustrated in the animation on the right, consists of 3 portions that maneuver the LCS from 2.5 kilometers below the ISS to the grapple point 10 meters below the ISS. For each of these trajectories, the time of flight was selected in order to minimize the delta V needed to perform each of these maneuvers. Upon reaching the 10-meter hold point, the LCS will disable all its thrusters and enter into free drift. Next, Asha will discuss ISS entry.
We decided to plan for our samples to enter the ISS rather than remain attached outside so that samples may undergo scientific experimentation or rideshare with astronauts to Earth in a human return vessel. Our preferred option is Plan A, where the Canadarm2 performs a track and capture procedure from the Kibo picture before directly handing off samples to the GEM RMS small fine arm. The other 3 backup plans appear in the report. Here we can see a ConOps diagram for Plan A. Let's start by zooming into Step 1. During Step 1, the LCS enters free flyer mode with disabling attitude control before the Canadarm2 tracks and captures the LCS from the Kibo power data grapple fixture, latching onto the LCS's flight releasable grapple fixture. Once grappled, the LCS will eject its solar panels with spring-loaded latches to reduce its profile. This ejection will occur in the aft direction, sending the solar panel into a lower, slower orbit. Going back to the overview, we can now zoom into Step 2. In Step 2, the Canadarm2 will raise the lunar communication satellite such that the GEM RMS small fine arm can latch onto a sample container. Each sample container has a standard microfixture for the small fine arm to grasp. This process will be done with the aid of both main truss cameras and Kibo external facility cameras. Going back to the overview, we can zoom into Step 3. Finally, during Step 3, the GEM RMS small fine arm will place the sample container onto the Kibo slide table, which clamps the container and engages a slide rail to bring the samples inside the airlock. This process occurs one sample container at a time. Once the sample is inside the airlock, astronauts can repressurize the chamber and retrieve the samples. Steps 2 and 3 repeat for the second sample container. Finally, the second sample container is safely inside the Kibo module. The Canadarm2 will place the LCS below the ISS and eject the spacecraft bus with the help of onboard thrusters. As mentioned, the LCS solar panel and spacecraft bus will be ejected from the Canadarm2. These kinds of ejections will occur routinely on the ISS, whether it be for trash removal or cube satellite deployment, such as the recent removed debris satellite. In addition, a 2.9-ton pallet was recently ejected from the aft direction using the Canadarm2. This pallet has no propulsion of its own and cannot be removed, just like our ejected solar panel. Yet Mission Control was able to place this pallet in a safe decommissioning orbit with a lifespan of 2 to 4 years before re-entry. A similar procedure can be followed for our solar panel ejection. Note that the solar panel's high area to mass ratio makes it more susceptible to drag and thus easier to bring down. Now that we have finished covering our solution, let's look at the budget. RASC-AL defines the mission budget to be no more than $1 billion per year between years 2022 and 2028, totaling $6 billion. Then, using NASA's project cost estimating capability, the total mission cost was estimated to be $1.5 billion in fiscal year 2022 dollars. This result was compared to the advanced mission cost model shown on the left. Interestingly, the 2 models have strong disagreements, most apparent of which is the estimate for the Lunar Transfer Vehicle. The PCEC estimates $415 million for the cost to manufacture and develop the 2 lunar transfer vehicles. The ANCM predicts nearly $1.36 billion in fiscal year 22 dollars. This disagreement is likely due to the rough estimate and fee parameters inputted into the AMCM compared to the PCEC. In addition to using the AMCM and PCEC models, we generated a rough order of magnitude estimate using a self-created cost estimating relationship. The graphs above are constructed using heritage missions costs for notable NASA lunar and Martian rover missions. The entire mission cost is divided by the mass of one particular object of interest to form a total cost to launch and operate per kilogram relationship. These estimates are shown above. Note that this model does not capture the ascent and return portions of our mission architecture and is thus an underestimation. Even still, this result supports the idea that the AMCM and PCEC results are in a reasonable neighborhood. Given our mission schedule, we mapped the budget over time to create a NASA Gantt chart. You can see the distribution of the budget per year and by mission division. Note that there is not a single year that reaches a cost greater than $500 million, and thus our proposed budget remains within the constraints of $1 billion per year between years 2022 and 2028. Thank you for listening. We're happy to answer your questions.